Hello everyone. Thank you so much for taking your valuable time for attending this session today. My name is Deepthi Goguri, and first of all, I would like to thank you for giving me this wonderful opportunity, Damir, to present for you user group for the second time. And thank you also for giving me the opportunity to present for Data Weekender as well this Saturday. And I'm also moderating this track one, just in case I just wanted to advertise you as well. So what are we going to discuss in this session today? We are mainly talking about the indexes, like method behind the magic of indexes in SQL Server. So this particular session is not a performance tuning session, but it's a session that is a dive deep topic where we'll dive deep into the query optimizer itself to know how indexes actually look like behind the scenes and what goes under the covers inside SQL Server. So there is a lot of content to grab. So before even getting started, let me tell you this. Please be seated. Do not move here and there, not even for a minute, because once you move for a minute and come back again, you might not understand the presentation because all my slides are or all the animations and how the process will happen um, under the covers, right? So there are no much of a word slides. All I have is couple of like 2 to 3 word slides. That's all. So come in the complete 1 hour session, we will be talking about what happens at the data page and the index page level. So yeah, so I just wanted to put that thing before even getting started. A little bit about me. I'm a database administrator with several years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology here in United States at Eastern Illinois University here in Chicago. And I do blog for dbanuggets.com. That's my website, and it's a very active website. I do blog 2 blog posts a week. I usually dive deep into the internals of SQL Server. So if you are really interested in knowing more about it, please visit my website. And I'm also a co-organizer for 2 groups. One is the Microsoft Data and AI South Florida user group, where we mainly focus on Azure and AI. And I'm also a co-organizer for Microsoft Data Diversity, Equity and Inclusion Group. And I'm a volunteer for Data Platform Women in Technology group as well. And if you would like to interact with me later, please contact me via Twitter at dbanuggets is my user ID on Twitter, and down below that's my email address. Like if you have any questions regarding this session later, or if you wanted to get in touch with me, please do not hesitate to contact me. So what is the agenda for this particular session today, right? We are not going to talk about the performance tuning, like we are not going to discuss if seek is better than the scan, or how many number of indexes can we exactly add onto the table to see that performance boost. We are not talking about any of that, but what we are going to do is we are going to dive deep into the query optimizer itself to know how index pages actually look like, and if at all you are inserting any data into the table, how that insert will actually affect the index pages and how SQL Server should have take that additional steps to maintain those indexes. And we are directly going to see that how that will actually happen at the page level. And we are also going to see how SQL Server will use the indexes to get back the data as quickly as possible. So why should we even care, right? Why should we care about knowing the internals of SQL Server? Knowing the internals of the indexes exactly. So before even talking about the indexes and stuff, let me talk about a little bit about myself. When I started my career as a DBA, while I try to learn about the indexes, when I read these articles, blog posts, all of them mention the B tree structures where we have 3 different levels, right? The root level of the index, intermediate pages, and the leaf pages. But whenever I see those leaf pages and intermediate pages, I know they are interlinked between each other and how the SQL Server will navigate to get into the exact page where the data gets stored. but I never understood how they actually look like at the page level, how SQL Server actually manage the index at the page level, how the data actually look like at that leaf level of the index or intermediate level. So until couple of months ago, I didn't know that, but once I came to know about it, I couldn't stop it. Because this is so interesting, I thought to put this thing together as a presentation and to share it to the world. So that's why here I am today. As a DBA or developer, we have several questions in our minds running all the time. Like for a table, how many indexes should we add? Or should I create a single index and add all the columns of the table into it? Or should I create an index and add a single column to each and every index, right? And when you run the query and when you see that actual execution plans for your queries, you see those beautiful things get popped up in the green color saying recommended index. If you go ahead and run this query, you'll get that 95% of the performance boost. But do you think if you directly go ahead and execute that query directly into your management studio onto the server, do you think you are actually improving the performance or decreasing the performance without you even knowing about it? Because SQL Server might actually telling you to just add that one little column of that table to your already existing index. But instead, if you directly go ahead and execute the entire script, you might be actually duplicating your already existing index. And now SQL Server have to take those additional steps to go ahead and manage both of these duplicate indexes at the same time, right? It takes so much of resources for SQL Server to manage these indexes. And we are going to see that how SQL Server have to manage the index in our coming slides. So I can promise you that by the end of this session, you are able to answer all of these questions by yourself. Like by the end of this session, then the next day, whenever you are going to create any index on your table, you will get that thought like, will this particular index, right, that I'm creating will actually benefit or will it degrade the performance? And you will be especially careful to add any columns into the index. Not that I'm not saying that you will be scared to create the index itself, but then you will take that additional steps in looking into what you're doing, So I can promise you that. So from now on, all you are going to see is these kind of pages on your screen, and we are not going to see any more word slides. So this is how the SQL Server data pages and the index pages look like. They look alike when you compare with the data pages and the index pages, they look exactly the same. So whenever you insert any data into the table, that particular actual data gets stored inside the page, which is of 8 KB in size. Even the index pages are 8 KB in size. So there are three parts in a data page or the index page. The top part of the page is known as page header, which will contains the page number, previous page number, next page number, how much free space does that page have. Those kind of metadata information is actually get stored at the page header information. You might be asking me why we need to have the previous and the next pages, right? Because SQL Server, take the example of an index, right? We will be sorting the index in the ascending order or in the descending order. So if you wanted to access the index, SQL Server should have a way to know to which page it have to go to next, right? If it is in the ascending order or if it is doing in the descending order, it have to know where it have to go next, to which page it have to go next. And all of these pages are most of the time they are physically ordered, right? So indexes are in the sorted order, and the data pages should also be interlinked between each other because SQL Server have to know where to go next. That is the reason we have these two pointer information. When you see the intermediate page, the space of the page, you see those 12 boxes. Those 12 boxes are the slots where our actual data gets stored, where our actual column data gets stored. So Whenever you insert any data into the table, that data will actually get stored in these slots, which is known as payload area. So, and why I'm mentioning only 12 slots is that we need to understand easily, right? For our demonstration purposes, I just mentioned 12 slots. That doesn't mean that SQL Server page in the real time it only have 12 slots, but just for our easy demonstration purposes, I have mentioned only 12 slots. And when you see at the bottom of the page, you see those little boxes which are known as row offset array. Row offset array meaning they have the pointer information pointing back to where the exact column data gets stored inside the payload area of the page itself. So how do SQL Server read that? SQL Server will read the row offset array from right side to the left side. And whenever we are searching on any data from a table, SQL Server directly cannot go ahead and get that data directly from the payload area. It cannot do that. It do not have a way to do that. But instead, what SQL Server will do is it will directly go ahead and get the row offset array pointer, which is actually pointing to the data itself at the payload area of the page. That's how SQL Server will actually access the page. So when you see on the right side top corner of the page, I have mentioned two indicators. The square, which is light blue in color, represents the data page, and the purple color rectangle with a downward arrow represents the index page. So why I mentioned these two indicators at the top right corner of the page? Because in the coming slides, all we see is these pages, right? So whenever you get confused of like, what is she even talking about, right? If you are in that situation, please go ahead and see whether I'm talking about the data page or the index page by looking at these indicators of that particular page. And I will be referring these pages by page numbers, and I will be, as we insert the data into these tables, we will be updating the previous and the next page pointers. So just keep that in mind. We are going to create a brand new table known as flowers. Now, why I mention flowers is because I'm a woman. All women love flowers. So just for fun, I just created the flowers. I am pretty much sure that this table doesn't make any sense whatsoever, but then it is serving the purpose of our presentation, right? That is the reason I created a table named flowers, and we have a couple of columns mentioned here, which is like ID, flower name, owner, code of the flower, and then entry date. So this particular table is actually a heap table, meaning we do not have any clustered index on the top of the heap table, but then we can go ahead and create a non-clustered index even on the top of the heap table, right? And before going into the page level details, let me tell you this. So whenever we create any brand new table to the SQL Server will go ahead and allocate a brand new page, which is like it will go ahead and get that unallocated page from the disk subsystem, and it will be allocating to the table, because now we need to have pages to the table, right? So it will allocate a page that will be allocated to the table, and then that table to be grabbed into the buffer pool to do the modifications. Whenever you are going to insert, update, or delete whatever operation you are trying to do, even the select, SQL Server directly cannot go to the disk subsystem and do the modification at the page level. It cannot modify the data at the page level on the disk subsystem, but instead it have to grab those pages, put them in the buffer pool, modify the data over there, like insert, update, or delete, and then once that data get updated into the page on the buffer pool, there is this process known as the checkpoint process, which will be running every minute by the SQL Server automatically. That particular checkpoint process will flush all these dirty pages back to the database, back to the disk subsystem, and harden them onto the disk. That's the regular process. So why I am saying this? Because we are going to insert the data. SQL Server cannot go ahead and modify the data pages on the disk subsystem. So we need to grab that into the buffer pool. So for our demo, we need a buffer pool, right? So for our demonstration purposes, we are taking very little buffer pool. Like we can only fit 3 data pages or the index pages together, only 3 of them into our buffer pool. That means 8 KB times 3 is 24 KB, right? We can only fit 24 KB into the buffer pool. Now I know you might be thinking me as crazy. What is she even talking about, right? But then if I tell you, okay, now our our buffer pool has 2 GB of size, right? How many pages can it fit, right? It can fit some thousands of pages, and I can't fit on my screen in that slide. I can't show you thousands of pages because we are talking about the page level, right? We are seeing the process, how it happens at the page level. So I can only fit 3 pages on the screen so that you can see. Now, why I'm explaining this again is because some of the other attendees from the other presentations has told me like, Deepthi, why is only 24 KB? SQL Server won't even start if we have the buffer pool memory of 24 KB. Yes, I know about it, but then we are talking about the internal stuff, right? So we can only fit in a couple of pages into the buffer pool. So that is the reason only for our demonstration purposes, we are taking 24 KB into our buffer pool. So you might be asking me, how about if we are going ahead and inserting more and more data into the data pages? We cannot fit in more and more data, right? More and more pages into the buffer pool because we can only fit 3 pages. In that case, just like the SQL Server, how we do in the real-time scenarios, in the real-time scenarios, SQL Server will go ahead and evict the least recently used pages out of the buffer pool. In the same way, SQL Server is going to evict the least recently used pages out of the buffer pool even here as well. So our table is currently the heap table. So even though it is a heap table, we can go ahead and create the non-clustered index on the top of this table, right? So let's go ahead and create the index name owner on the flowers table with the 2 key columns of the index, which is the flower name, comma, owner. So our key columns of the index are these 2. So as I told you that SQL Server will go ahead and allocate a page for the data page. And if you have any indexes, SQL Server will also go ahead and allocate a page for the index as well. So it will allocate a page number 11 for the data page and page number 12 for the index page. Now you might be asking why page 11 and 12, why not page 1 and 2, right? So whenever we create any table, SQL Server will first go ahead and allocate a couple of pages for the metadata itself. Those are called metadata pages like IAM page, GAM page, you know, right? Those are the pages which will actually contain the metadata information about all the other pages of the table. So once it allocates those couple of pages, it will go ahead and allocate the pages for the data pages and the index pages. So for our demo, we are taking page number 11 and page number 12. So you might be saying that 1 is to 11 and 1 is to 12. Now what is the 1, right? The 1 represents the database file itself, which is the primary data file, right? The MDF file. Let's go ahead and insert the first record into the table flowers, which is acacia best and the other column information. Now, as we have the brand new page, data page and the brand new index page, we can go ahead and insert the data into the data page, page number 11. When you observe here, the first slot is representing 30,5 zeros. Now, what is that number, right? 30 represents the size of the record itself, and the 5 zeros which you are seeing after the comma represents the bitmap. So how do SQL Server read that? 5 zeros represents the 5 columns, right? We have 5 columns in this particular table. So each 0 represents each column value. If there is a value in that particular column, that bitmap will be represented as 0 for that particular column. But if we have a nullable value that needs to be stored inside the page, SQL Server doesn't want to waste the space at the page level. So it will go ahead and it will go ahead and manage those nulls instead of storing them at the payload area of the page. Instead, it will go ahead and update the bitmap value from 0 to 1. Let's take an example, right? Let's say the date of entry for the last column is null that we are going to insert. Then SQL Server doesn't want to store that value at the payload area, but then it will leave that slot empty, and then it will change the bitmap value for that particular column from 0 to 1. Now that is the beautiful way of SQL Server saving the space at the page level. And when you see the bottom of the page, you see that row offset array is actually pointing to the first slot, right? So SQL Server, how do it read the page? To get the data from this particular page, it will directly go and see the pointer information at the row offset array. So it is pointing to the first slot, right? So that's how it will go ahead and get that record information from the payload area of the page. So once we inserted the data at the data page, we should also maintain the index, right? So we need to insert the index columns, like the key columns of the index, into the index page as well. So we have the index on the flower name comma owner. So we are only going to insert those two key columns into the index as well. So let's go ahead and do that. So now if you see the first slot on page number 12, you see that 6,00. 6 represents the size of the record itself of that particular Acacia best from the index page. 00 after the comma represents the values of Acacia and best. Now you have a pointer information pointing back to the data page. Like if you wanted to go and do select star from flowers where flower name is Acacia and owner is best. If you wanted to do such kind of select statement, then we wanted to go ahead and grab all the column information, right? So if SQL Server will go ahead and use the index to grab the information for that particular query, it have to go and interact with the data page as well, because we also wanted to get that other column information for Acacia best. So how do it get that? If SQL Server have to interact with the index, it will go ahead and directly see that pointer information pointing back to the data page and the slot number. So 1:11 represents the data page itself, and the 1 at the end of that pointer, it represents the row offset array, which is actually pointing to the first slot, right? That's the pointer information. And even though the data pages and the index pages both will have the row offset array pointers. Now let's go ahead and insert another record into the table, Erica Newton. Now we have space on page number 11, so let's go ahead and insert Erica Newton into the data page. But once we insert the data into the data page, we should also insert the key columns of the index into the index page as well. So let's insert Erica Newton into the index page. Now let's go ahead and insert one more record, Daisy Stamp. Do we have space on the page number 11, which is the data page? No, right? So SQL Server will go ahead and allocate an unallocated page from the disk to the table, and from the table, it have to directly grab into the memory, right? The buffer pool to insert that particular record. So SQL Server allocated a page, and SQL Server will assign a page number 13. But then as we are adding the pages, the previous and the next page pointers should be also added to the pages. So on the page number 13, the previous page will be pointing to page number 11 because that's the data page number, right? And on the page number 11, if you see, the next page will be pointing to page number 13. And now we have a brand new page. So let's go ahead and insert Daisy Stamp into the page number 13. So as we inserted the data into the data page, we should also maintain the index, right? So let's go ahead and insert Daisy Stamp into the index. But then if you observe the row offset array information at the bottom of the page, page number 12, the first slot is pointing to Acacia best. The second slot is pointing to 9th slot, which is Daisy Stamp. Now, why is that? is because the last entry which we have done is starting with D, Daisy, right? The flower name starts with D, Daisy. Now, when you see the first record inside the index page, the first slot is pointing to Acacia, and the second record physically, right, it is pointing to Erica. But then we just inserted Daisy stamp. It should go ahead and actually fit in between Acacia and Erica, right? But then SQL Server, it doesn't have any way to physically modify the data at the page level physically. So that is the reason it have to somehow logically modify the data in the order of the key columns of the index. So how does SQL Server will do that? Is by modifying the pointer information at the row offset array in such a way that they are ordered in the order of the key columns of an index. Now, if you see the pointer information, it is first pointing to Acacia, the second slot is pointing to Daisy, and the third slot is pointing to Erica. And that's how the index have to be ordered, right? Because it is ordered in the ascending order of the key columns of an index, and this is perfect now because it cannot physically modify the data. It is logically modifying the data at the row offset array. Now this is how our index pages and the data pages look like. Left side your screen, we have two data pages, 11 and page number 13, and those two pages are interlinked between each other. The double-sided arrow represents the previous and the next page pointers pointing back and forth. And when you see the index page, we just have one index page, page number 12. And let's go ahead and insert Gardenia Golf into the table. Now, do we have space on page number 13? Yes, we do. So let's go ahead and insert Gardenia Golf into page number 13. But then we have to also maintain the index, right? But do we have any space on page number 12? No, right? So how do we fit in Gardenia Golf into the index? SQL Server, it will go ahead and allocate one more page for especially for the index, right? Because we are trying to add a record into the index. So it will go ahead and allocate a page for the index, and that page have to grab into the memory to do this particular insert, right? But then SQL Server will also do something else at the same time. Because we are keeping on adding the index pages right now, we are trying to add a new page. As you know, the index is a B tree structure, and there should be a page which is a root page, which have the pointer information pointing back to these two pages at the leaf level. Now, page number 12 we have right now. We are trying to add a brand new page to insert Gardenia Golf, but then to maintain the hierarchy, SQL Server have to create a brand new page which will become the root page. Now let's go ahead and see that in action. So how many pages do we need to evict here? We need to evict two pages, two least recently used pages, because we are trying to add two new pages, one for the leaf level and the other for the root level. So let's evict two pages. These are the least recently used pages. SQL Server allocated two new pages. It will give the page number 14 and page number 15. Page number 14 will be the leaf level of the index, and page number 15 will become the root page. So as we have the brand new page, page number 14, the previous page should be updated, which is page number 12, and on the next page on page number 12 will be updated to page number 14. So we have brand new page here. So let's go ahead and insert Gardenia Golf here. But then the brand new page got created for the root page, right? So that root page should contain the pointers information pointing back to page number 12 and page number 14. So how do SQL Server read the root page? Any flower name equal to Acacia and less than Gardenia have to go to page number 12. Any flower name equal to Gardenia or greater than Gardenia have to go to page number 14. That's how SQL Server will read it. Now this is how the index pages look like right now. Previously, we just had page number 12, but then we continuously keeping on adding the data. So it should also maintain the index, right? So we created a brand new page, page number 14, and then a brand new complete new page got created, which is page number 15. That will be the root page, having the pointers pointing back to page number 12 and page number 14. But when you see the data pages, we still have two data pages, page number 11 and page number 13. Now let's go ahead and do our first select star from flowers, where flower name is Erica. How do you think SQL Server will process this query? Do you think SQL Server will use the index, or do you think SQL Server will just go ahead and scan the entire table? Let's not assume anything, but then let's go ahead and see what SQL Server will do. If SQL Server will use the index, right, it will have to first interact with the root page of the index, which is page number 15. Let's say Erica is actually pointing to the page number 12 of the leaf level of the index. First, it will contact page number 15, and then page number 15 is pointing to page number 12. It will go directly to the row offset array pointer pointing back to the payload area information of the page number 12, and then at that particular payload area, at the slot information of the page number 12, it will actually have a pointer pointing back to the data page, because we are asking for select star, right? So it will have to interact with the data page. Let's say it will interact with page number 11 to get that Erica information, right? Select star from. So how many pages should SQL Server read if it have to use the index? 3 page read, right? Because it have to first interact with page number 15, page number 12, and then page number 11 or page number 13, depending upon where the pointer information pointing back to the data page. So it have to do the three page read. But instead SQL Server will think, why should I even go ahead and use the index, because I just have 2 pages for the table itself. Let me go ahead and scan the entire table, because we just have 2 pages. 3 pages reads is greater than 2 page read, right? It costs less resources for the SQL Server to go ahead and scan the entire table. So it decides to scan the entire table. So first it have to access page number 11 and then page number 13. It have to scan the entire page. Page number 11 is not in the memory. So let's go ahead and evict page number 12, get the page number 11. It will scan the entire page and found a Erica over here. But then SQL Server doesn't know if there is one more Erica in the next page, because we are scanning the entire table, so it have to scan the next page as well. So when you see the next page pointer at the header information of page number 11, it is pointing to page number 13. Page number 13 not in the memory. So evict page number 14, grab page number 13, it will scan the entire page. But then we just have one Erica, it won't find anything on page number 13. That's how SQL Server will intelligently do this table scan instead of interacting with the index. So by this, we understood that scans doesn't mean that they are bad, right? If at all you see those scans, table scans in your queries, you can go ahead and see why SQL Server choose to do the scan instead of using the index. You might be having couple of pages on your table. That's why SQL Server might have actually choose to do the table scan. So scans doesn't mean they are always bad, right? Let's go ahead and insert Bergenia Wade into the table. So do we have space on page number 13? No, right? So let's go ahead and insert one more brand new page. SQL Server will allocate a brand new page, and that page should be inserted into the buffer pool. But then we have to evict page number 15. SQL Server will give the page number 16, and then previous and the next pages should be updated. Previous page is page number 13, and the next page on page number 13 is page number 16. We have a brand new page, so let's insert Bergenia Wade. But then we should also maintain the index, right? So which page do you think SQL Server should access first? Page number 15, because SQL Server don't have any way to directly go ahead to the leaf levels without interacting with the root level of the index. So we need to evict page number 11, get the page number 15 right in between your screen. Page number 15 is inserted into the buffer pool. So page number 15 is actually showing that Burgundy weight has to fit in on page number 12. Page number 12 not in the memory, so evict page number 13. Page number 12 left side your screen is in the memory, page number 12. So do we have space on page number 12 to fit in Burgundy weight? No, right? So what SQL Server will do right now? Root page is actually showing that Burgundy weight has to fit on page number 12, but then page number 12 is completely full, the leaf level page, right? The leaf level page of the index. So there is something known as page split that is going to happen right now, because root page is actually showing Burgundy weight has to fit in on page number 12, but then we do not have space. So page split happens right now, meaning a brand new page will be created at the leaf level somewhere in the primary data file, somewhere in the primary file group. But then half of the data from the page number 12 has to move into the new page, and then that new page will get exactly, like, it will be brought exactly beside the page number 12, because that's a page split. It should fit in just beside the page number 12. That's called the page split. But then once half of the data, like approximately 50% of the data, once it gets moved from page number 12 to the brand new page, page number 12 will have enough space to fit in Burgundy weight onto page number 12. Now you might be asking me, why page split? Why can't SQL Server directly go ahead and create a brand new page, and why not we fit in Burgundy weight onto that page, right? But then if you observe, the root page is actually pointing to page number 12, and page number 12, if you see, Burgundy starts with B. And if you wanted to physically keep the data intact in the order of the key column of an index, then definitely Burgundy weight has to fit in onto page number 12. It can't go to the brand new page, because physically that can't be in the ordered structure, right? So it have to fit in on page number 12, and that is the reason a page split happened. Let's go ahead and see that in action. Let's affect page number 16. A brand new page got created during this splitting process. A page split happened. Brand new page, give it a page number 17. Previous page number should be page number 12, because that brand new page will be created just beside the page number 12, exactly in between page number 12 and page number 14. Because previously we had two leaf level pages, right? Page number 12 and page number 14. But now as the page split happened, page number 17 will be exactly fit in between those two pages. So the pointer information will be actually modified accordingly. So on page number 12, previous page will be page number 12 on page number 17, if you observe. And on page number 12, the next page pointer should be updated from page number 14 to page number 17. We will do that later, but if you observe the page number 17, the next page should be pointing to page number 14, right? Because that's the next leaf level page. This page got created exactly in between those two pages. So half of the data should be moved, right? So approximately 50% of the data, which is highlighted in the maroon color, will be moved to page number 17. So we have space on page number 12 to fit in Burgundy weight into page number 12. But then we have to update the pointer information on page number 12, pointing to the next page, which is not 14 but then 17. And we should also update another pointer on a different page. Do you know which page it is? That's page number 14, which is the previous last leaf level page, right? So we have to evict page number 15, get page number 14 into the memory. And if you see there, the previous pointer on page number 14 is still pointing to page number 12. But then that have to be updated to page number 17, because that's the page which got created right in between these two pages, right? So all the pointers have been updated, but then the brand newly created page, which is page number 17, during this splitting process, right? That that page can't just hanging there without any connection to the root level page of the index. There should be a pointer information pointing back to this particular newly created leaf page, right? So we need to update a pointer information on the root page as well. So we do not have page number 15, which is our root page in our index. So let's evict page number 17. Page number 15 is in our memory right now. So we have to update a pointer pointing back to page number 17. So a pointer information is updated. And how does this look like in the structure wise, right? This is how it looks like in the structure wise. Previously, we have only two leaf level pages, which is page number 12 and page number 14. But then we try to insert Bergenia Wade into leaf level of the index, and root page has actually shown that Bergenia Wade has to fit in on page number 12. But then page number 12 is completely full. So a page split happened and a brand new page got created, which is page number 17, exactly in between page number 12 and page number 14. And the pointer information has been updated back and forth. And then Bergenia Wade has got that space because half of the data from the page number 12, approximately 50% of the data has moved to page number 17, so that page number 12 have the space to fit in Bergenia Wade into the page number 12. And then page number 17 can't just hanging in there without any connection to the root level of the index, right? The page number 15. So a pointer information has been inserted into page number 15, which have now connection to the page number 17 as well. And now we have 4 index pages and 3 data pages. Let's go ahead and insert Kalmia Morris into the table. Now, do we have any data pages over here? You can see the indicators on the top. All are the index pages, right? So we need to grab the data page. So let's evict least recently used page, page number 12. Page number 16, right side your screen, is in the memory right now. So we do have space. Let's fit in Kalmia Morris here. And then we have to also maintain the index, right? We have to also insert Kalmia Morris into the index page, leaf level of the index. But which page do we need to contact first? Because we do not know where to fit in at the leaf level page. We do not know which page it is. So we need to interact root page of the index, which is page number 15. Page number 15 pointing to page number 14. Luckily, page number 14 is already in the memory, right? On the left side of your screen. So let's fit in Kalmia Morris into page number 14. Sometimes it's easy to fit in all of these records maintaining the index in the memory itself, right? If you have those pages already in your memory, it will be easy for SQL Server to maintain those index. Now let's go ahead and do these two statements, like observe these two statements for a minute and see if there is any difference between them. We do not have any difference between them, right? The only difference we have here is in the where clause, those values that we are asking for flower name and owner name are just interchanged between them. But then the queries are exactly the same. When you execute the query, we get the exact same results, right? So from the SQL Server side, it is very easy for the SQL Server to go ahead and remodify these, order of these where clauses, these predicates in the order of the key column of the index. Our key column of the index is on flower name, comma owner. So the second statement, SQL Server, it is very easy for it to remodify that by converting that into flower name and owner name, because that's the order of the key column of an index, right? So how do SQL Server will access this information and how do we get the results? Since in the where clause, we are asking for the key columns of an index, right? So SQL Server will definitely use the index, but then we are asking for select star from. So we will go ahead and grab the information from the leaf level of the index, but then we will connect to the data pages as well to get the other column information from the data pages. So if SQL Server will use the index, definitely it will use, because in the where clause we have those key columns of the index, right? So first it will interact page number 15, which is the root level page of the index. It is pointing to page number 14, which is the leaf level of the index. Leaf level of the index is pointing to data page, page number 16, slot number 2. Page number 16, right side your screen, it is already in the memory. Luckily, it is pointing to the slot number 2 of the row offset array, which is pointing to 7th slot. 7th slot is Kalmia Morris. We have asked select star, so it will get all the rest of the column information by contacting the page number 16, which is the data page. That's how SQL Server will actually use the index to get back the data as quickly as possible. Now let's go ahead and insert one interesting record where we have a nullable column. For the date of entry, we do not have any value. We are giving the null value. So how do SQL Server will insert this particular record, right, at the page level? Page number 16 is completely full, so SQL Server will evict a page, get that brand new page, give it a page number 18. Previous page should be updated to page number 16. Next page on page number 16 should be updated to page number 18. So let's go ahead and insert funnel Hibbert. But then the fifth column, if you observe in the slot 6, is completely empty, right? Now, in the beginning of the session, I told you that SQL Server will actually update the null values instead of saving them at the payload area. It will directly go ahead and update the bitmap value from 0 to 1, to just save the space at the page level. Now here in our demo, we just saved one slot, but in real time, you might be having some hundreds and thousands of null values, right? That might be actually saving a couple of space to fit in couple of more records at the data page level. Now we have to also maintain the index, right? We have to also insert funnel Hibbert into the leaf level of the index as well. Now how do we do that? First, which page should the SQL Server access first? Yes, that's the root page, page number 15. Page number 15 not in the memory, page number 15 in the memory right now. It's left side your screen, page number 15. Page number 15 is actually pointing to a leaf level of the index, page number 17. Page number 17 not in the memory, evict page number 16, page number 17 in the memory, right in between your screen. So we do have space, right, to hit funnel Hibbert. And now this is how our index pages look like and data pages look like. Data pages, we do have 4 pages, 11, 13, 16 and 18, and index pages, we do have 4 pages. Now let's go ahead and see how SQL Server will process this query. Select star from flowers where flower name is Kalmia and owner is less than or equal to Morris. Actually, our key columns of the index is in the order of flower name, owner. So first SQL Server will find the flower name Kalmia and then it will search through the other rest of the where clauses, which is the owner. First, it will have to access page number 15 because it is going to use the index. So page number 15 is actually the root page is pointing to page number 14, the leaf level page number 14. Page number 14 is not in the memory. So let's evict page number 18, page number 14 in the memory. So page number 14 is actually pointing to page number 16. Now why we have to actually interact with data page is because we are asking for select star, right? Select star meaning we have to get that additional column values by interacting with the data page. So it's pointing to data page number 16 slot number 2. 16 page number is not in the memory, the data page. So let's evict page number 17. Page number 16 right side your screen, it's in the memory right now. It is pointing to the second slot. Second slot is pointing to the 7th slot in the payload area of the page, which is Kalmia Morris. That's how SQL Server will actually use the index. This time, let's do a little bit different, right? Select star from flowers where owner is Morris and flower name is less than or equal to Kalmia. How do SQL Server process this query? Since our key column of the index are in the order of flower name, owner, it will have to go ahead and first search on the flower name which is asking for less than or equal to Kalmia. The last entry into the table is Kalmia. So that means SQL servers have to go ahead and search on each and every flower name which is less than or equal to Kalmia, meaning it have to access each and every page of the index. So it will first go to the page number 15, and then it have to go ahead and search on each and every leaf level of the index as well, because we are asking for all the flower names which are less than or equal to Kalmia, right? So first it will access page number 15. Let's say first it will go to the page number 12. From the page number 12, it will directly go to the row offset array, the first pointer. It will point to the information at the page number 12 inside the payload area, and it will get that pointer information on the page number 12, which is actually pointing to the data page, and slot number on the data page, right? So let's say it is actually interacting with the page number 11, which is the data page. On the page number 11, it will directly go to that slot number and see which where it is actually pointing to on the page number 11, get that record information, come back to the page number 12, which is the leaf level page again of the index, check that second slot value on the row offset array on the page number 12, go and find the the page pointer on the page number 12. Let's say it is again pointing to the page number 11, right? It will go to the page number 11, check that second slot, get that column, get that row from there, and then come back again to the leaf level page, page number 12. Once it completes the page number 12, it will go to the page number 17. And that way it have to go ahead for each and every record which it have to access the data page. It have to go back and forth to find this particular information for to process this particular query. It has to at least do some hundreds of the page reads to process this query. Instead, SQL Server will think, why should I even do this hundreds of page reads? Instead, let me go ahead and scan the entire table, because we just have four pages for the table itself. So let me go ahead and scan the entire table, which is containing only 4 pages, right? So first it will go ahead and interact with page number 11, 13, 16 and 18 to process this query. Now how do SQL Server will do that is by first getting the page number 11, right? Page number 11 not in the memory, evict page number 15. Page number 11 left side your screen is in the memory right now, so it will scan the entire page, and then it have to scan the next page. If you see the next page on page number 11 pointing to page number 13, page number 13 not in the memory, so evict page number 14, page number 13 right in between the screen, it's in the memory, so it will scan the entire page. The next page to the page number 13 is page number 16, the next page, right? So it will scan the entire page, and then it have to scan the page number 18. Page number 18 not in the memory, so evict page number 11, page number 18, it will scan the entire page. So while it is scanning the entire table, it will find the Kalmia Morris on page number 16. That's how SQL Server will intelligently decide to do the table scan instead of using the index and going through all of those, all of those it have to interact with all of those levels in such a way that it have to read some hundreds of pages. So instead it thought it would be better to just scan the table. Let's go ahead and insert Hibiscus Roberts this time. We do have space on page number 18, so let's insert Hibiscus Roberts here. But then we have to also maintain the index. So which page should we access first? Page number 15. Page number 15, evict page number 13 to get the page number 15 left side your screen. It is actually pointing to page number 14. Page number 14 not in the memory, so we have to evict page number 16. Page number 14 left side your screen, it's in the memory. Yes, we do have space to fit in Hibiscus Roberts here. So currently we have 4 data pages and 4 index pages. Now let's go ahead and insert Carnation Preston into flowers. Now do we have space on page number 18? No, right? We just have that one slot left because previously we had inserted that null value, and SQL Server has actually maintained that in the bitmap, right? Instead of storing the value of nulls at the page level. So we cannot fit in that particular record here. So SQL Server will go ahead and evict page number 15, allocate a brand new page, give it a page number 19. Previous page should be updated to page number 18. Next page on page number 18 should be updated to page number 19. We do have space on page number 19, brand new page. Let's insert Carnation Preston here. But then we have to maintain the index. Which page should we access first? Page number 15. So page number 15 not in the memory. Page number 15 is in the memory right now. So which page it is actually pointing to? It is actually pointing to page number 12. Observe very carefully here because something going to happen here. So page number 12 not in the memory. Page number 12 right now in the memory, and then yes, we do have space, so it will fit in Carnation Preston. So something will happen in the next coming slides. We do have 5 pages right now. We just added one data page, page number 19, right? We still have 4 index pages, but then 5 data pages. Now let's do this particular query now. Very simple and very easy to the SQL Server. Select flower name, owner from flowers, order by flower name, owner. How do SQL Server will do this query? Since we have the index on the key columns flower name, owner, SQL Server will just directly go and scan the entire leaf level of the index, and it do not even have to go ahead and touch the data pages because we are not asking select star, right? We are only asking for the key columns of the index. So it is very simple, very easy for the SQL Server to process this query. And also we are asking for order by. Index is already in the sorted order, right? So it's very simple. So which page should SQL Server access first? Page number 15. It will scan the page, go to the leaf level pages, page number 12, the first page. It will scan the entire page and then go to the next leaf level of the index, which is page number 17. Page number 17 not in the memory. Evict page number 19, page number 17 in the memory. It will scan the entire page. That's a leaf level page of the index, right? And the next page we have is page number 14. Page number 14 not in the memory, so evict page number 15. Page number 14 in the memory, so it will scan the entire page. That's how SQL Server will actually go ahead and process this query very simply, just to get those columns directly from the leaf level of the index. It doesn't have to touch the data pages at all. Now let's go ahead and insert Jasmine Acosta into the table. This is how our index and the index pages and the data pages look like. Nothing changed. But then we have to insert, right? Do we have the data page here? No. So we have to grab the data page into the buffer pool. Page number 12, evict. Page number 19, it's in the memory right now. So let's go ahead and insert Jasmine Acosta into the data page. But then we have to maintain the index. So something is going to change here right now. Very interesting. So which page should we access? Page number 15. Page number 15 right now in the memory. So it is actually pointing to page number 14. But when you observe page number 14, which is already in the memory, left side your screen, it's completely full. So what SQL Server will do? Because this particular Gardenia Golf has to fit in on the page, right? But then this page is completely full. So SQL Server will again do the page split. Page split meaning a brand new page gets created, giving a page number 20. Previous page should be updated to page number 14 because that's the page split, and this page is directly going in between, like right beside the page number 14 because that's the page split, right? And the next page on page number 14 will be updated to page number 20. Half of the data should be moved to page number 20 so that Hibiscus Roberts will be fit into page number 14. But then we created a brand new page, right? It can't directly hanging in there without any connection to the root page. So we need to update a pointer information on page number 15. But then do we have space on page number 15? Page number 15 is completely full. So what SQL Server will do again? It have to do page split one more time, meaning a brand new page will be created again, giving a page number 21, and previous page number should be updated to page number 15. On page number 15, the next page has to update it to page number 21. Now you might be thinking, but Deepthi, page number 15 is our root page, right? It's no more root page because page number 15 is also split and a brand new page got created. A page split happened, meaning it is no more one page. It is two pages right now. So, but we have to create a one more page, which will be our new brand new root page, because root pages are always one page. They are no more two pages, right? So root page should always be one page. So our page number 15 will be our X root page, no more our brand new root page, current root page. A brand new page should be created, which will become the root page, which will actually have the pointer information pointing back to these two pages. These two pages, page number 15 and page number 21, will become our intermediate pages of the index. So let's go ahead and see that in action, right? So we just created a brand new page. Half of the data from the X root page should be moved to the page number 21, and then another brand new page should be created because page number 21 can't hang in there without any connection to the root page. We do not have any root page, so SQL Server will go ahead and create a brand new root page, give it a page number 22. We do not have to update any more pointer information here on page number 22 because we just have one root page, right? It do not have any previous and next page pointers, but then it will have the pointer information pointing back to page number 15 and page number 21. How do this actually look like in the structure? This is how the index look like in the structure format. When you see, previously we just had 3 leaf level pages of the non-clustered index, page number 12, 17 and 14. But then we try to insert a record which should be actually going to the page, different page number, but then on 14 it have to fit, but then we do not have any more space. So a brand new page got created, a page split happened, page number 20 got created, and then it have to be, a pointer information has to be updated into the root page, right? But then page number 15 is actually full. So a page split happened again on page number 15. Half of the data moved to the brand new page 21, and then the pointer information has been pointed for the page number 20 on page number 21. And then a brand new page got created, which is a brand new root page, which is page number 22, which have that pointer information pointing back to page number 15 and page number 21, because those two pages are now our intermediate pages of the non-clustered index. If you see the data pages, we still have 5 data pages, but then we are going to change that, right, by adding the clustered index. Before adding the clustered index, let's go ahead and do the last select statement. Select owner from flowers where flower name is Jasmine and ID is 5. How do you think SQL Server will process this query? We are asking for one of the key columns of the index, which is the owner, and we are searching on one of the key columns of the index, which is flower name, the first key column of the index, right? But then we are also searching on ID column. But do we have the ID currently in the index? No, right? So SQL Server, while it is trying to get this information of the owner for the flower name Jasmine, it have to also search on the ID, which is 5. That means currently it have to go ahead and search on the page where this particular flower named Jasmine is actually there. So it have to actually contact the data page, right, where that ID 5 is there. So let's go ahead and see how SQL Server will do this. It will first access the page number 22. That's our brand new root page. So that's actually pointing to page number 21. Page number 21 is the intermediate level of the index. Page number 21 is actually pointing to page number 20, which is the leaf level of the index. Page number 20, not in the memory, evict page number 15. Page number 20, right in between your screen, it's in the buffer pool right now, right? So it's actually pointing to data page, page number 19, slot number 2. Now why we have to interact with data page? Because we are only asking for owner, right? But in the where clause, we are also asking for where ID is file, and currently we do not have ID inside our index page, right? Inside our leaf level of the index. So it have to contact page number 19. Left side your screen, it's already in the memory. Slot number 2 is actually pointing to Jasmine Acosta. But then we are asking for ID number 5, but we have ID number 10 here. That means SQL Server has to navigate through all of these leaf level, intermediate level, root level, intermediate level, leaf level of the index, and then interact with the data page to find nothing, right? Because we were asking for ID 5, but then we do not have any ID 5. So we did all this work for nothing. But then currently let's go ahead and add the clustered index, because we wanted to see how clustered index itself look like, right? So let's go ahead and create the clustered index on the ID column. Now how does clustered index root level and intermediate level look like? This is how they look like. I know it's confusing, but let me go ahead and explain it clearly. From left to right, the page number 23 and page number 24 are the intermediate level of the clustered index. When you see the page number 25, it's the root level of the clustered index. For example, let's take the intermediate page, page number 23, left side your screen. All it contains is the key column, the clustered key, meaning the ID column. All it have is the ID value and a pointer information pointing back to the data page itself where that ID is stored. If you see there, it have 1, 3, 5, 7, and on the next page of the intermediate level of the clustered index is page number 24. It have the ID value 9 and a pointer information pointing back to the data page where that particular ID value is actually stored. When you see the root level page, page number 25, all it contains again is the clustered key, which is the ID column value, and then a page which is actually pointing to these two intermediate pages of the clustered index. Now you might be saying, you are saying that it will actually point to the data page where that ID is stored. So that means data pages are the leaf level of the index, leaf level of the clustered index. Yes, they are. SQL Server will not create any brand new pages for the leaf level of the clustered index, but then they are the data pages itself in the sorted order of the clustered key, in the sorted order of the ID column. What I mean by that is, I mean this. The leaf level pages of the clustered index are the data pages itself in the sorted order of the ID column. If you see the data inside the page number 11, you see that ID columns like 1, 2. On the page number 13, 3, 4. On page number 16, 5, 6. On the page number 18, 7, 8. On the 19th, 9, 10. That means the data has actually beautifully sorted out. SQL Server had that wonderful opportunity once we created the clustered index. It has that opportunity to go ahead and reorder that rows physically in the sorted order of the ID column, because we have created clustered index on the ID column, right? So they are all in the sorted order. And these data pages are the pages at the leaf level of the clustered index. They are just the data pages in the sorted order of the ID column. How do they look like? This is how the clustered index actually look like. When you see the leaf level of the clustered index, we have all the data pages, right? Page number 11, 13, 16, 18, and 19. Those are the data pages itself in the sorted order of the ID column, because clustered index is on our ID column, right? But then if you see the intermediate pages of the clustered index, we have page number 23 and page number 24. All these pages contains from the intermediate pages, these two pages just contain the clustered key, which is the ID, and then a pointer information pointing back to the data pages where that ID value got stored. And when you check the root level page, which is page number 25 of the clustered index, all that page contains is the clustered key, again the ID, and a pointer information pointing back to the intermediate pages which have that ID column again pointing back to the data pages where that ID value is stored. But then if you see the non-clustered index, it remains the same, but something will be changed here once the clustered index has been created on the table. What is it, right? When you see the leaf level of the non-clustered index, these leaf level pages of the non-clustered index, if you remember, they actually contain the first name, last name, and then a pointer information pointing back to the data page and the slot number. Do you remember? But then now once you added the clustered index, they don't directly point out to those data pages and the slot numbers at the data pages, right? It won't have any of those pointer information. All they contain is, instead of pointing to the data page and the slot numbers, they directly point out to the root level page of the clustered index. That means they have that ID column. Directly they have that ID column, the clustered key, at the leaf level of the index. Now how does that look like at the leaf level of the non-clustered index, right? These are the leaf level of the non-clustered index. If you look at the data, let's take the example of page number 12, right? Left side your screen. Instead of pointing to the data page and the slot number, it directly have the ID value, which is the clustered key. Now this clustered key will be pointing to the root level page of the clustered index. From there, it will navigate through the data pages where that actual data gets stored for that particular ID column, right? Now these are all the leaf level pages. And when you see the page number 15 and page number 21, which are our intermediate pages of the non-clustered index, right? Now these two remain the same, like just if you observe them, they are directly pointing to the leaf level pages of the non-clustered index, right? So they do not change. Even the root page also won't change at the non-clustered index level. In the summary, what we have discussed here is we have dived deep into the query optimizer itself to know how the non-clustered index actually look like and how the clustered index actually look like. We have seen how the data pages and the index pages, how they look like and how the data gets inserted into the data pages. And once we insert the data into the data pages, how does that insert actually affect the indexes, right? SQL Server have to take that additional step to go ahead and maintain those indexes. So how many indexes you have, those many changes that SQL Server have to do at the index as well. It have to go ahead and maintain all these indexes at the same time. So we have also seen the SQL Server, like how we have used the indexes to actually get back the data as quickly as possible. So just imagine if you have any duplicate indexes, right? How much time and resources it takes for the SQL Server to go ahead and maintain all these duplicate indexes at the same time. And do you have any performance benefit from that? No, right? In fact, you are actually affecting the performance. So keep this in mind and please make sure that you do not have any duplicate indexes on your tables. Just go ahead and look into all of your indexes, consolidate your indexes so that your queries would love to use those indexes, right? Unique indexes. Sometimes, if you have those data warehouse scenarios where you're actually inserting the bulk insert into the tables, in those scenarios, please make sure you disable the indexes because we keep on inserting the data in the bulk, right? So we do not want SQL Server to go ahead and do the insert at the same time, update all of our indexes at the same time. So please go ahead and disable all those indexes, do your inserts do your bulk insert, and then rebuild your indexes so that you will get that indexes brand newly created with all of this information instead of going ahead and updating those indexes, right? The index rebuild will actually help. So that's one of the point that I would like to mention here. So I think you enjoyed the session. So these are the resources I used to prepare my presentation. So if you would like to know more about the internals, please follow these. And if you wanted to get in touch with me, please follow me on Twitter, and I would love to interact with you. And you can also know what all other sessions I'm giving in the near future. And that's my website, dbanuggets.com. If you wanted to know more about it, please visit my website. And you can also contact me on LinkedIn as well. Once again, I would like to thank you so much for taking your valuable time for attending this session today. And I would like to thank each one of you for giving me this wonderful opportunity. Thank you so much, Damir, for having me today.